Going to discuss the dynamics of plates. So, we will be in the next few lectures we are going to actually discuss the vibrations of plates. So, today we are going to initiate some discussions on the modeling of plates. Now, what is a plate? We have seen that a membrane is a two dimensional continuum which does not transmit any bending moment. Now, when you think of a plate, it does transmit bending moment or it can resist bending. So, which means a plate is a two dimensional elastic continuum which resists or transmits bending moment. So, in order to first, where do we find plates? So, plates are found in various machines, in civil structures, etc. So, we are interested in first the dynamic model. We are interested in setting up the equations of motion or modeling the dynamics of plates. So, as it happens with any dynamic modeling, we make some simplifying assumptions so that we can have a two dimensional theory for plates. So, a continuum in two dimensions. So, what assumptions do we make to simplify our model? So, the first thing that we assume that there is a plane or there are fibers which are unstretched. So, these are called neutral fibers. So, we assume the presence of neutral fibers which occurs if you do not have in plane forces in the plate. So, there is the plate is not subjected to any in plane forces. Then you have when the plate undergoes small transverse vibrations, then there are fibers which remain unstrained. The second assumption we make is that there is no shear deformation. So, this is known as the Kirchhoff hypothesis. So, this corresponds to the Euler-Bernoulli hypothesis for beams. The third assumption we make to keep our model linear is that the slopes are small. So, when the plate deflects, the slope, because of this transverse deflection, they are small. So, we are going to model under these assumptions. So, let us first look at. So, let us consider a plate. And we look at a little element. in this plate. So, what are the stresses on this element? We will make the further assumption that the plate thickness is constant. So, this plate is lying in the x y plane, and its deflection is transverse to the to this plane. Now, we consider that the stresses that are acting are the normal stresses So, we have stresses sigma x x, sigma y y, these are normal stresses, and we have shear stresses, so sigma x y sigma x z and sigma y z. So, I am showing the stresses only on these two surfaces. Now, there can be a distributed force on the plate, but at present we are going to drop that. So, essentially we have only these stresses which are non-zero. Now, when we want to construct a theory in 2 dimensions, then we integrate over the thickness of the plate. We integrate over the thickness of the plate, and we define what are known as the stress resultants, the force and moment resultants. Also known as the stress resultants. So, the stress resultants due to the normal stresses So, these are because of normal stresses and this is because of the shear stress. So, this is in plane, and then we have the out of plane shear stresses, which we denote by capital Q x and capital Q y, and we have the moment resultants because of the moment, because moments due to the normal and the shear stresses. So, these are the in plane So, we have defined here m x as z times sigma x x, but actually this moment is along the y axis. So, but still we call it m x because it is a moment with sigma x x. Now, these resultants, they have the units of force per unit length or moments per unit length. Now, let us look at these force and moment resultants on the infinitesimal element. So, this is an infinitesimal element of the plate So, I will mark out the resultants. So, the first is n x. So, I will show the this face at x equal to 0, there you have n x in along the negative x direction, and on this face you have n x plus n x derivative with respect to x dx. So, this length is dx. Similarly, this is dy. So, this is the normal stress resultant on this face. Similarly, you have on this face Now, the resultant because of the shear stress on this face is up, on the other opposite face it will be down, that will be q x, and this is q x plus del q x del x dx. Similarly, here up, this is q y plus and the in plane shear stress resultant, which is n x y. So, this of course is similarly this will be now on the other two faces you can imagine that they will be without this additional part and they will be opposite in direction. So, that is these are the stress resultant or the force resultants. Now, let us look at the moment So, we look at the moment resultants now. So, here we have now this moment in this direction on the normal to this face is on this face So, this is the moment because of the normal stress sigma x x. So, that is going to follow this right hand rule. So, this is the moment on this face on the face x equal to 0 you have just m x in the opposite direction, and on this face it is because of sigma y y. So, you have these as the moment resultants. Now, we will come back to this figure again. Now, let us write down the constitutive relation for the material. So, these stresses are related to the strains. Now, since we have considered that the plate is infinitely stiff in shear, there is no shear deformation. So, there is no shear deformation of the element along the in any of along the z. So, now so therefore, the corresponding stresses actually cannot be calculated from any material constitutive relation. We have to determine them from the equations of motion. Now, let us look at the geometry of deformation. So that we can calculate the strain in terms of the deflection of the plate. So, let us consider the plate initially undeformed, represented by this dashed curve, let us say along the x axis, and this deflects in this manner. So, if this is a line which is initially along the z, so it is vertical, then this line deflects to this configuration. So, the displacement in the direction of x can be written approximately, if you call that displacement as u, is minus z times del w del x. So, it is as you know that del w del x is tan of this angle. So, tan, and for small theta this is also equal to and that is equal to theta. So, if z is the location of this point from the neutral line, neutral surface, then the deflection in the direction of x is given by minus z. del w del x. Similarly, for the y, in the y direction, we can write now. Using this, we can calculate the strain field. So, that is the strain field. Now, if you have this strains, so these are linear in z. Now, this w is independent of z. So, strain is linear in z. So, sigma x epsilon x x and epsilon y y are linear in z. So, therefore, sigma x x is also linear in z, as you can see from these expressions. So, that will be linear in z. So, if you go back to this calculation of the resultants, if this is linear in z, then z integrated from minus h by 2 to plus h by 2 is actually 0. So, which means that these terms are going to vanish. So, these are n x, n y and n x y, they are all 0. So, the non-zero resultants are q and m. So, let us calculate then m, because q will ultimately come from the equations of motion. So, the moment resultants if you recall, this is the expression. So, if you substitute, so use this expression of the stress where these strains are written from here, and if you substitute in this expression and simplify, then you can see that this leads to similarly so here d and of course, nu is the Poisson ratio. And E is the Young's modulus. So, these are the moment resultants. Now, we can write down the equations of motion. So, the first, so we write down the transverse equation of motion in the transverse direction. So, if rho is the density of the material and h is the thickness, so this is force per unit, this is mass per unit area times the area of the little element times the acceleration. So, if you now look at this figure, so we have in the transverse direction these forces Q. So, here it is upwards. So, here there will be a downwards which will be minus of q y in the equation of motion. So, you are left with, and since remember these are all forces per unit length. So, this and from this the contribution is, so these are the forces in the transverse direction. Now, let us look at the rotational dynamics. So, for that we will refer to this figure. So, I will directly write. So, this is the del w del x is the small angle. So, this is the rotation about the y axis. So, this double derivative with respect to time will give us theta x theta y double dot. So, rotation about the y. So, angular acceleration about the y axis. So, this equals, so we have these moments So, because of so it is a rotation about the y axis. So, we have first this moment, then we have the moment this one because of y x. So, let me write this then. And because of this force q x, you have another moment. So, this is the rotation about the y. Similarly, you can write down the rotational dynamics about the x axis, and this is the, so I is the moment of inertia per unit area. So, for this element, we have I equal to rho h cube over 12. So, these two equations correspond to the rotational dynamics, whereas this equation, of course, I will divide this whole thing by dx dy. So, this corresponds to the transverse dynamics. Now, I am going to eliminate q x and q y in the transverse dynamics using these expressions. So, if I do that, so this is what I obtain. Now, here I will replace this these moments using the expressions that we have derived, the moment resultants in terms of the field variable. So, if you do that, then you can simplify the equation. This can be written as so the Laplacian of w del square w del t square plus d. Now, this turns out to be so this is written as, so we can write this in a compact form. So, this is the equation of motion of the plate. So, here nabla 4 is the square of the Laplacian. Now, we need to talk about the boundary conditions. So, this model, the way this is known as the Kirchhoff-Rayleigh plate model. If you, this is the rotor inertia term, this is because of the bending and this is the inertia term. So, if you drop this rotary inertia term, assuming that the moment of inertia is very small, In that case, if you drop this term, then you have the Kirchhoff plate model. So, if you drop the rotor inertia term, then you have the Kirchhoff plate model. With the rotor inertia term, it is called the Kirchhoff Rayleigh plate model. So, now we discuss about the boundary conditions. So, we can have various kinds of boundaries. So, suppose let us consider a clamped So, suppose you have a plate and you have a boundary here which is clamped boundary. So, if the boundary is clamped, this is actually quite simple, then the displacement must be 0 and of course, the slope must be 0. So, these are geometric boundary conditions. Then if you have a simply supported edge at x equal to a. So, we have the displacement as 0 and the moment equal to 0. So, this implies if you use the expression of the moment, but if the edge is simply supported and is straight. So, that W is at x equal to a for all y is 0, then there is no curvature. So, this term is also 0. So, this will imply now this is a natural boundary condition. Now, we come to this interesting case of a free boundary. So, we have discussed clamped boundary and simply supported boundary. Let us discuss the free boundary. So, if a plate has a free boundary, then intuitively we may guess that. So, this is suppose this is x equal to a. So, this boundary is at x equal to a. Intuitively we might guess that. So, this shear stress resultant. So, this q x is going to be 0. So, q x is along z on this face. So, that should be 0. The moment equal to 0, and in addition we have another moment because of the shear stresses, in plane shear stresses, that also has to be put to 0. But you see, this differential equation of the plate is 4th order. Now, so it cannot support 3 boundary conditions at an edge like this. At a boundary, it cannot satisfy 3 boundary conditions. So, there must be something wrong about these boundary conditions, at least some of them. So, there must be some combination. So, now we are going to discuss how they are actually combined. So, let us see this m x y. So, let me refer to this figure once again. So, this was m x y on this face, let us say at x equal to a. So, this is m x y. Now, this is a moment because of the in plane shear stress. So, this moment can change as you move in the y direction. So, at another location, this can be m. So, I am considering 2 locations separated by a small distance epsilon. So, we are moving in the y direction. So, this is the moment at a location, a distance epsilon along the y. Now, this can be equivalently represented as a couple. So, this can be replaced by a couple, and similarly this can be replaced by another couple. So, therefore, at this point you can imagine that this the resultant the force resultant here can be which is now a transverse force is given by So, all these things are calculated at x equal to a. So, this is an additional edge a resultant force which is in the transverse direction, which is same as q x. So, we can combine now this must be 0. This is defined as the edge force. This is known as the edge force. So, this edge force must vanish. So, it is a combination of the force because of the out of plane shear stress and the moment because of in plane shear stress. So, these two they combine to give us what is known as the edge force. So, we have the boundary conditions as this and this, and if you write these down in terms of the field variable. So, and if you calculate this edge force, so these are the boundary conditions for the free edge at x equal to a. So, let us summarize. So, we have looked at the equation of motion of small amplitude small slope vibrations of flat plates. So, plates are two dimensional elastic continuum which can transmit or resist bending moment. So, we have looked at the equation of motion and the boundary conditions, and we have for the standard boundary conditions which are the clamped and the simply supported, the boundary conditions are quite simple, whereas for the free boundary we have discussed about the edge force that must vanish. So, so the boundary conditions for the free boundary have to be carefully determined. So, with that I conclude this lecture.